We have learned the concept of constant acceleration in our previous video. In this session, we are going to learn the concept of centripetal force. Let's imagine a car is traveling on the straight road in the right direction with constant velocity of 5 meters per second. As the velocity is constant, the change in velocity as per acceleration formula is zero, so the acceleration is zero. This is what we learned till now. Now, let's say the same car, after traveling in a straight road, is now traveling in circular path, as you can see in the picture. And the speed of the car is still 5 meters per second. Now tell me whether the velocity of the car is constant or not. The answer is no. But how? Do you remember that the velocity is vector quantity and speed is scalar quantity? Even if the speed of the car is constant, the direction of the car is continuously changing. As the velocity is both magnitude and the direction, velocity of the car is not constant. Now, when the velocity is not constant, the acceleration of a car is not zero. The direction of the change in velocity is constantly changing and the direction is inward towards the center of the curve. As the direction of changing velocity is in the inward direction, the acceleration is also in the inward direction towards the center of the curve. The car is accelerating towards the center of the curve and hence the direction of the car is changing on the curve path. Let's learn how the direction of the car is changing from straight line to curve direction. So, here, imagine, a car is traveling on circular path. The speed of a car v1. The direction of the velocity v1 is in the straight line. After some time, actually a fraction of second, the velocity is v2 and the direction of the velocity has changed, as you can see in the figure. The same change can be observed as v3, v4 in the figure. The direction of the velocity is constantly changing. Here, the magnitude of the velocity is constant. Magnitude of v1 is equal to the magnitude of v2, v3 and v4. Here, let's find out the direction of changing velocity. Let's draw the velocity vector separately. So, the velocity vectors can be separately drawn, same like on circular path. Here, the size of the vector is magnitude of the velocity, so all the vectors are of same size and the direction of the velocity is changing. v1 is initial velocity and v2 is velocity after some time. The resultant vector can be drawn as change in velocity. If we draw the resultant vector at the position of v1 on circular path, we can observe that the direction of resultant velocity vector is inward towards the center of the curve. In the same way, the resultant vector of v2 is also in the inward direction towards the center of the curve. And the same can be observed in the direction of resultant vector of v3 and v4. So, if we draw the direction of resultant vector of constantly changing velocity, we would see that the direction of the resultant vector of constantly changing velocity is towards the center of the curve. As the resultant velocity vector or vector of changing velocity is towards the center of the curve, the acceleration would also act in the same direction. Also, it can be seen that the resultant velocity vector is perpendicular to the direction of velocity v1, v2, v3 and so on. Now, remember the Newton's first law of motion. If there is change in acceleration of the body, it is possible only if there is net force acting on the body. So, here the net force is acting on a car in the direction of the acceleration, that is towards the center of the curve path. This net force which keeps the car in circular motion, which is pulling the car towards the center of the curve, is called the centripetal force. How this force is created and what exactly developed this centripetal force. It cannot be just imaginary kind of thing. Let us try to understand how this force is developed by taking some practical examples. Let's imagine the car is moving on curved path. As we have learned, a car must be accelerating inwards towards the center of curve. And this acceleration is developed due to some net force acting on a car. As a car makes a turn, the force of friction acting upon the turned wheels of the car provides centripetal force required for circular motion. It is the friction between tire and road, which provide the centripetal force. Let's imagine a car is moving in a straight road, and is about to take a turn. When it is about to take turn, it tends to slide straight, that is, outward relative to the road. If the car is moving on ice, this is the path to be followed by a sliding car. To stop sliding, friction must act inward. Now, before sliding starts, to oppose the outward relative motion, static friction between tire and the road comes to play. This force of friction opposes the motion by acting in opposite direction, that is, radially inward to the turn. So, here in case of car moving on curved path, the static friction will play the role of centripetal force. Now, let's take another example, say, satellite moving around the Earth in circular motion. Satellite has some velocity, and let's say it is constant velocity, rather the magnitude of the velocity. If there is no acceleration or net force in the inward direction, satellite would escape in the space. It is the gravity of the Earth which attracts the satellite towards the center of Earth, provide the centripetal force which causes satellite to move in circular motion around the Earth. Now, let's take another example. Say, stone is tied at one end of string and you are moving the same in circular motion. Stone will have some velocity which is in perpendicular direction to the radius. It is the tension in the string which acts as centripetal force which causes the stone to move in circular motion. And we can feel that tension in the string while moving the stone in circular motion. Subscribe Extra Class Academy for more educational content.